Hi! Today we are going to talk about a legendary game, Unreal Tournament 99. And we will try to do something a little crazy. We will try to run it in the browser. But not only run it, we will try to run it in multiplayer mode. And here is the best part. We do not have the original source code of the game. But still, we will make it work. Before we start, let me quickly introduce myself. I am a fan of retro games. I also work professionally on porting games to the browser. I started with ports of games like Dune 2 and Transport Tycoon. Later, I created JS-DOS library that can run DOS in Windows 90X programs directly in the browser. I published my ports on my website, DOSZone. Over time, the website became more visible and a small community appeared around it. We started to push more games in browser. Here you can find our Telegram channel, where we post news about our project. Please follow us. And last year we brought Heroes of Myth and Magic 3 to the browser. I think everyone knows that game. It's a true classic. After that, DOSZone became much more popular. People started to contact us. Some wanted to publish their own ports on the website. Some wanted to show their browser experiments. One of those projects was Half-Life Deathmatch. It was developed by Evgeny Akhmanyuk. It is a browser port of Xesh 3D engine, but not just a simple port, it's a deep rework. For example, it has asynchronous texture loading. It also has full multiplayer based on WebSocket technology. It is a very cool project. If you're interested, you can go and play it. After that, James Darpinian contacted us. He offered to publish his browser version of Quake 3 on DOSZone. His version also works in the browser. It also has multiplayer, but it uses WebRTC. So we added that too. Then we ported Quake 2, and suddenly we had a very interesting set of classic shooters. We had Half-Life, we had Quake, we had some work in progress around Counter-Strike. So almost all the legendary multiplayer games from that period was there. But one game was still missing. You can probably guess which one. It was Unreal Tournament. At that point, the idea was obvious. Unreal Tournament also had to run on our portal. But how we do normally port a game to the browser? Usually we have the source code. Most often it is a C or C++. Then we compile it with mscripten. Mscripten produces WebAssembly, a JavaScript bundle, and some support files. After that, we can run game in the browser. If everything goes well, it works on all major platforms. That is the normal way. But Unreal Tournament was different. With Half-Life and Quake 3, we had open source code or open source reimplementations. So everything was clear. But Unreal Tournament 99 was not released like that. Epic Games didn't publish the source code, so the big question was, what can we do if we have no source code? There is one interesting story here. In 2017, Ryan Gordon, who worked with Epic, got permission to publish a compiled browser version of Unreal Tournament. He was not allowed to publish the source code, but he was allowed to publish the compiled build. So, he compiled the game for the browser and put it on his personal website. That build is still available. If you open it, you can see a great demo of the game. You can reach the menu. You can watch the intro. But Ryan clearly said that this was only a demo project. It contains only part of the game data, about 200 megabytes. The full game is much bigger, around 600 of megabytes. So the demo can reach the menu, but after that things may break, because many files are missing. The port was made with SDL, AMScript and graphic compatibility layer Regal. And yes, if you open the web demo, go to the menu and try to start the game, it crashes almost immediately. The browser shows some strange error. At first, the reason seems simple. The author already said that the demo does not include all game data. So our first idea was, Maybe we only need to add the missing game files. For a WebAssembly project, this is not too hard. Usually, such projects look like a normal web page. You have an index.html file, you have an index.js, index.wasm, and you have the game data. So in theory, we only need to copy the files to the website and package the data correctly. There was even a GitHub project that helped add data to the demo, build and generate a ready-to-run project. But there was a problem. Unreal Tournament has a virtual machine inside the game. The game runs scripts written for this virtual machine. These scripts are compiled by a special compiler called UCC. And the compiled scripts are not always compatible between different versions of the game. So we had to find the exact data that matched this exact browser build. And this was difficult because nobody really knew which Unreal Tournament version Ryan had compiled. It looked like a build from somewhere between official releases. But after some research, our friend Nikita found the data that matched. We added the data, and yes, the demo module started to work. We could run a demo session. But there was another problem. If we changed almost anything in the menu, the game crashed. For example, if we changed deathmatch to capture the flag, or even if we change the player skin, or if we select another level, sooner or later it crashed. And every time the error was the same. Exception catching is disabled. This is typical error come from mscripting. It happens when you compile game with disable exception catching enabled. It means that exception handling was disabled during compilation. Let me explain it in simple terms. In C++, a program can throw an exception. Normally the program has a try block and a catch block. The main logic runs in the try block. If something goes wrong, the program jumps into the catch block. Then the game can handle the problem and continue working. This is normal behavior. But if exception catching is disabled, the catch block is removed. So when an exception happens, the game cannot recover. It simply stops. Why would anyone use such a danger option? The answer is performance. The browser port was made in 2017, and that time WebAssembly did not yet have native try and catch instructions in the standard. Mscripting had to emulate exception handling through JavaScript. The extra layer was slow and heavy, so disabling exception was a reasonable choice if you wanted more performance. Today, this is a less of problem because WebAssembly has better exception support. But we could not just rebuild the game. We did not have the source code, so we were stuck with the compiled WebAssembly module and the generated JavaScript bundle. At this point, I wrote to Ryan. I asked him if he could give us the source code, or at least if he could make a new build with exception catching enabled. To my surprise, he answered. He said he could not share the source code because the agreement was still active. But he said he will try to make a new build with exceptions enabled. Unfortunately, we never got that build. Maybe he did not have enough time. Maybe the old toolchain was too hard to restore, I don't know. We had to work with what we already had. We had a WebAssembly module generated by mscripting. And we had JavaScript bundle around it. Here, browser development gives us one big advantage. Native developers often work with programs that crash somewhere inside a binary. They can collect a crash dump. They can try to reproduce the crash later. But in the browser, we have a very powerful debugging environment. We can put breakpoints in JavaScript. We can also put breakpoints in WebAssembly. We can inspect memory. And we can stop programs almost anywhere. So in theory, we can debug everything. I opened the JavaScript bundle generated by mscripting and found the place where exceptions were thrown. I added a breakpoint here. But the result was not very useful. The call stack only showed request animation frame again and again. This happens because many browser ports work as one repeated frame function. The browser cannot block the main thread, so the game schedules one frame, then another frame, then another frame. By the time we reach the outer error handler, the original useful stack is already gone. But we can search using original error message, and we can find exact place where original error is thrown. It happens because this code is generated by Emscripten. This is 6a throw function. It's a function from exception handling emulation layer. And here you can see the real stack of the error, and now you can navigate to function that call this 6a throw. And as you see, there is a lot of functions, but you can navigate them and see real WebAssembly code. Each instruction is simple: load a value, store a value, compare two values, call another function, jump somewhere. But globally, it is very hard to understand. There are thousands and thousands of instructions. At first, I spent a couple of days trying to understand what was happening, and I didn't understand much. So I wrote to Nikita and said, I think this project will not work. It is too difficult. We may need a month just to understand this build. I was ready to close the project and move on. But Nikita was very motivated. He really wanted Unreal Tournament to work in the browser. So he continued to experiment. And then he found something important. For example, if you open the game menu, then open the game console, and type a command like openctf face, then add bots, and then press escape, the game works. This was a very important discovery. It proved that the game logic itself was not completely broken. The missing catch block was not always critical. At least the training mode with bots worked. We also tested other mods. They worked too. So the main problem was not the game engine. The main problem was the user interface and some code path around it. At the moment, I decided to give the project another chance. But we need a clear plan. The plan was: first, learn how to launch a game without the UI. Second, learn how to launch the server mode. Third, learn how to launch the client mode. Fourth, connect the client to server. And if all of that worked, polish the result and publish it. So we started. Emscripten always generates a JavaScript bundle. The bundle usually exposes a global object called module. Module has several standard hooks. One of them is pre-run. It allows you to run your own JavaScript before the WebAssembly program starts. We changed this part of the generated code. We removed the automatic call to main function. Instead, we created a small startup script for the game. In that script, we set the game resolution, we set the player name, and the most important line was a command like start dem agony listen. This tells Unreal Tournament to start a map in listen mode. In other words, it starts a local game server. Now we had a script, but Unreal Tournament expected this script as a file. WebAssembly doesn't have a direct access to the real file system, but Emscripten provides its own virtual file systems. And it has a documented API. One useful function is create data file. It allows us to create a file inside the virtual file system. So we create an out.exe file in the game system folder. Then we started the game and told it to read and execute this file. The game tried to start and of course it crashed with exactly the same message as before. But this time the logs were useful. The game really tried to create a server. It failed because of a socket error. So the next problem was the network layer. Emscripten implements part of the Linux POSIX API. This includes functions for networking: socket, connect, send, receive, close, and others. Emscripten implements them through a layer called socketfs. This layer maps C or C++ socket calls to JavaScript, to WebSocket-based behavior. But in our build, there was a problem. It was a release build. Most function names were stripped. The function still existed, but the names were not human readable. Instead of names like socket or receive, we had names like 3, 4, 7. Before replacing anything, we need to understand which functions was which. So we had to rename functions back to meaningful names. To do this, let's try to understand the structure of a WebAssembly module. A WebAssembly module has sections. There is type section. For example, a type can say, this function take 3 integer and return 1 integer. One type can be reused by many functions. There is a data section. It contains static data, such as string. For example, strings like true, false, or none can be stored there. This section is useful because you can search it and find hard-coded strings from the game. There is an import section. WebAssembly cannot directly call the browser DOM API. It doesn't know what the browser is, so if WebAssembly needs something from JavaScript, it imports a function. For example, it can import a function for working with frame buffers. And so we can understand that real frame buffers is function 177 in WebAssembly. There is also an export section. This is the opposite. It allows JavaScript to call functions from WebAssembly. And here we see 2487 function is a some global sub function. And finally, there is a function section. It contains functions, it contains the type of function and the body of function that contains actual instructions. Here we see a zero function. And if we look into export section, we see that zero function is actually stackalog function. So we want to rename 0 to 0 stackalog. But 0 is not a real name of the function. If you run a program and put the breakpoint into this function, you will see different name in a browser. You will see 490 as a name. This happens because this pseudocode is generated by disassembler, and disassembler use name 0 for this function because it needs to refer this function from other places. And so he imagined the name 0, but real name doesn't exist, and 490 is the index of this function in WebAssembly. So I created my own naming scheme. The name contained the function index, the disassembled name, and the meaningful name that I assigned it. This way I could find the same function in 3 places: in the original binary, in the disassembly text, and in the modified output. For editing WebAssembly I used Binarian. Binarian is one of the main tools used in the scripting ecosystem. It can read WebAssembly, build an internal representation, modify it, optimize it, and write it back. It is written in C++, which is not always convenient, but it works well. The naming function is conceptually simple. You load the WebAssembly module, you have a mapping of old names to new names, you find each function by its old name, then you assign a new name. You also need similar logic for imports and exports. After that you save the module again. This worked. And now we could rename functions. During the whole project I renamed only about 16 functions. And it doesn't sound like much. There were many more imports and exports. So only 8% of functions were renamed. But even a small number of good names helped a lot. If you continue reverse engineering a project professionally, you can keep renaming more and more functions. But for our task, 16 important names were enough. So, we have learned how to rename arbitrary Wasm functions. Let me remind why we need this. We faced a problem where the game did not start because of networking issues, and we need a way to deobfuscate functions. Now we can do this, and we can replace the sockfs layer. We created a new file called net.js, then we found the place in index.js where AIM-scripting creates socketfs. This is standard part of AIM-scripting output, so it is not too hard to find. We change the code like this. If Windows Net exists, use our implementation. Otherwise, use the default AIM-scripting implementation. The default implementation is very general and quite complex. I made a much smaller implementation. At first, I added only the functions that the game needs right now, just stubs. Then I started the game again. It crashed, but now it called our createSocket function, and we could see useful arguments. The game tried to create an IPv4 socket. The socket type was UDP, the protocol was UDP. Here we can recognize POSIX socket function. Is even more interesting is that in the stack trace we can see a human readable name syscall 102. Let's take a look at this function. From the name it was clear that this was a system call. Inside it there were many cases. Each case matched some POSIX socket operation. By looking at the arguments, it is easy to guess that the first case is a create socket and case 12 is a receive message. There are 17 functions inside this call in total. It is easy to rename a wasm function. If we set a breakpoint inside it, we will see that function 6707 is receive message. This way we can mark all POSIX functions because all syscalls follow the same pattern. But anyway, the game still crashed because our socket implementation was only a stub. CreateSocket was returning an empty value that was not suitable for the game. I fixed this function so that it returns the correct structure expected by AIM-scripting. There is no much interesting here. This is just a class from socketfs that describes the socket type, its address and the standard functions. So we added more functions. We added getSocket, bind, send message, receive message and close. One important detail is receive message. If there is no data available, it should not return a fatal error. It should return error code 11. In POSIX, this means something like there is no data right now, try again later. This is normal for non-blocking sockets. So our receive message returned error 11 when the socket queue was empty. After this, the game moved. As you can see, it creates two sockets. But it still crashed in another place. So I searched for a way to get more logs from Unreal Tournament. And I found that you can start the game with options like log and no home dir. This makes the game print much more debug information. I enabled that and started the game again. This time the error was clear. The game tried to call setSockOpt. It wanted to enable broadcast mode on the socket. And games often do this to search for servers on the local network. But WebSocket doesn't support UDP broadcast. So the default network layer reported an error. Let's go back to our syscall. As we can see, only two cases return this error. From the arguments, it became clear that case 14 is getSockOpt and case 15 is setSockOpt. The Unreal Tournament called getSockOpt to check if broadcast mode was enabled. It got a negative answer and then the game crashed. The fix was simple. In our implementation we said, yes, broadcast mode is supported. In reality, we did not need real UDP broadcast for our browser version. We only need the game to continue. So let's try this fix and try to start the game. This was a big moment. The engine started completely without the UI. The log showed that the match mode was running, the game was waiting for players. And because we had logging in our socket functions, we could see that server was constantly trying to read data from the socket. So the server loop was alive. Next, we need to start the client. Starting the client is much easier. You only need a command like open IP address, and port. Port is 47 is a standard Unreal Tournament port. We run the client. It's surprised the game did not crash, but it printed a network error. The problem was that the client tried to bind to port 0. In POSIX, binding to port 0 means, please choose any free port for me. But our stub implementation returned port 0 again. The game didn't like that. It expected a real port, so it crashed. The fix is simple. We need to change our bind implementation. So if address was not set, we set it. If the port was 0, we assigned a real port ourselves. Then we updated the socket information. After that, the client started sending message. You can see this in logs. So we had a working server, we had a working client. The next step was to connect them. My first idea was simple. Let's put two iframes on one page. Run the server in one iframe, run the client in another iframe, then pass network packet between them using post message. I implemented this quickly, and of course, it didn't work. At some point, the game waited in a loop and did not release the browser event loop. This has created a deadlock. Both sides were waiting. The tab froze. So I switched to WebRTC implementation. WebRTC can work very well for multiplayer, but for debugging it was a bad choice. WebRTC is very complex. When something breaks, it is hard to know what is broken. If is WebRTC broken? Is the game broken? Is the signaling broken? Is the network broken? So it is too many variables. Later, while preparing this talk, I realized that there was a much better option for local debugging: broadcast channel. Broadcast channel lets two browser contexts exchange messages. For example, two tabs on the same browser can talk to each other. For our case, this was perfect. We created a channel called UT99, then we created message queues. One queue was for the server port, another queue was for the client port. If packet was sent to port 7, we put it into the server queue. Otherwise, we put it into the client queue. Send message is implemented in trivial way. Just put the message in right queue and that is. Receive message is also simple. If the source port is 7, we read from the server's queue and pass the data back to the game. Otherwise, we read from the client queue. If the queues are empty, we return error 11, so the game continues to work correctly. Let's test it. We started the server and we started the client. The client worked, but the server crashed. And this was painful. We had already done so much. We had started the game without UI. We had started the server. We had started the client. We had connected them together. But now the server crashed again with the same kind of exception as it was in the beginning. And the worst thing, there was no useful information in the console. So we're back to the original problem. And this means we had to dig deeper. Let's go back to the root of our problem, the 6a throw function. What can we do with this exception? I think we can simply avoid calling throw and hope that the game will continue to work. I tried that. The game still did not work, but now we got more information. There was an assert on an object loading counter. The assert even printed a source file name and a line number. We searched for Unreal Tournament source code leaks. We found a lot of source code. But the exact line did not match any source version we had, so the source code did not directly solve the problem. Still, it helped us to understand the idea. The game had an object loading counter. When the game starts loading an object, the counter increases. When the loading finishes, the counter decreases. If an error happens, the catch block should also decrease the counter. But in our build, the catch block was removed, so the counter stayed too high, and later the assert failed. The assert was not the root case, it was only a symptom. We had to find the real exception that happened earlier. In Unreal Tournament 99, exceptions are thrown using a typical function called appthrow. Basically, it takes an array of strings. But in WebAssembly, strings are just bytes in memory. Mscripting provides helper function like UTF-8 to string, so we can read those strings directly from WebAssembly memory. We return it to the throw function and add a breakpoint there. When the breakpoint hit, we look at the color function. This function received two integer arguments. Most likely, they were string pointers. We tried to read them. At first, the data looked like garbage. Probably we were too late and memory had changed. So, let's restart the test case and read the values again. This time we got meaningful error object not found. That matched the engine logic. In a function called something like localize error was being called with the message object not found. So let's move it one level higher in the call stack and read more arguments. Here we already have 6 variables. Let's count them one by one. One of them was IPDRV, another was class, and another pointer to HTTP download. Now the road makes sense. The missing object was related to the IPDRV HTTP download class. In Unreal Tournament, IPDRV HTTP download is used for downloading missing resources. For example, if the client doesn't have a map or package, the server can redirect it to an HTTP download. But in our case, we did not implement that part. We only implemented the sockets. Luckily, Unreal Tournament allows this HTTP download system to be disabled in the configuration. If you disable it, the game can send resources through the normal network channel instead. That was perfect for us. So, we opened Unreal Tournament configuration and disabled the HTTP download classes. Then we started the server again. We started client again, and finally it worked. After 8 years, we managed to make multiplayer work in this old browser demo build. We did it without source code, we did it without help from Epic, we had no internal documentation. We only had the compiled WebAssembly module, the JavaScript bundle, the browser debugger, and lot of plugins. After that, we moved to polishing. We added bots, we wrote mutator that sent game statistic to our server, we prepared the page, and finally we released it. The best part was the reaction. People liked it, we received a lot of positive feedback, and even Ryan himself wrote that he was impressed by what we had done. So what is the main lesson here? For me, the lesson is simple. There is almost nothing impossible if you are motivated enough. WebAssembly is still just code. You do not have to be afraid of it. It may look strange at first. It may look like a huge wall of low-level instructions, but you can read it, you can debug it, you can patch it, you can rename functions, you can replace parts of the runtime. You can slowly turn chaos into something understandable. The browser is also a great environment for this kind of research. It gives you strong debugging tools. It lets you inspect JavaScript and WebAssembly together. It gives you fast feedback loop. The whole Unreal Tournament project took about half a year, but honestly, if I had accepted from the beginning that I needed to go deeper into WebAssembly, I think I would have solved this core problem much faster. Because in the end, the solution was not magic. The most important thing was not to give up. If you want to try the result, you can scan QR code on the left, and if you want to follow our future work, you can scan the QR code on the right and subscribe to our news channel. Thank you very much.